Okay. So we discussed on the shallow foundation using the EC7. Okay, the discussion on this shallow foundations in EC7 okay has been addressed in section 6. Okay. So in general, okay, the shallow foundations can be consist of pad, strip, and rough foundations. Okay, so there is common type of shallow foundation. Okay, so and some provision may be applied to deep foundation such as Kaizen. Okay, so but for our case, okay, we focus on the pad, strip, and rough foundations. Okay. So based on the limit state, okay, so the discussion on the shallow foundation, okay, should look on these several items under the limit state. Either it is failure, either it is ultimate or sufficiency limit state. Okay, so um, for the limit states that we need to uh, focus is on the loss of overall stability, okay, bearing resistant failure, failure by sliding, ground and structure combined failure, structural failure due to foundation movement, excessive settlement, excessive heave, unacceptable vibrations. Okay, so this is some of the example in diagrams. Okay, where we have the loss of stability. Okay, then we have a combinations of failure, either from ground or from structure or both of combinations. Okay, so then we have a structural failure. Okay, that we need to consider in the design. So design and construction consideration must be considered when choosing the depth of the sprit foundations, okay, due to the climate effects, okay, and also due to the shrinkage and swelling of clay, okay. So in some country, okay, due to the very cold season, okay, so the frost damage we contribute to the failure of the shallow foundations, okay. So at the same time, we need also to consider the surface of the available nearby this shallow foundation, okay, and also the nearby structure. Does it uh, provide any effect on this foundation? Okay, so another thing is the soluble material, okay, groundwater table, and also the adequate bearing stratum. Okay. So design requirement, the design must meet two principal requirements of the limit state. Okay, capacity insufficient to support load, avoiding excess settlement which might lead to a loss of function. Okay, so I guess the similar that we have discussed in the introduction part. Okay, so this limit state is known as the ultimate limit state and sufficiency limit state. Both states must be always be considered in the design. Okay, this philosophy is the basis of Eurocode 7. Okay, the concept related to shallow foundation can be shown in the figure below. Okay. Okay, so this is the conditions if what we call as if we apply, okay, a structure, superstructure on the top of the ground. Okay, so there will be two effect. Okay, either from the environment action. Okay, so in this example, the example is show a snow effect, okay, due to the environment. Okay, So we may have a wind, for example, wind effect as well, okay, due to the environment, okay. Then the dead load from the superstructure and also the live load, okay, from the superstructure will be transferred to the footing, okay. So the reaction from the soil will provide the bearing pressure, okay. So due to the load applied, okay, we have this kind of a curve, okay, which is the load versus the settlement curve, okay. So in this gray area, okay, so it is related to the limiting settlement, okay, and the working load that we apply on the structure, okay. So we provide the actual settlement, okay. So this is the bearing resistance, the ultimate limit state, okay. So means that normally this value has been divided into several factor safety, okay, in order to obtain the working load that could be applied on the soil, okay. So means that it's very difficult, okay, uh, uh, for the soil, okay, to fail, okay, after it's been applied for after being used the working load value, okay, unless if we use if we use a wrong value, okay, then it can exceed the bearing resistant value, the ULS, okay. So under the working load, okay, the problem is related to the settlement, okay. Perhaps if we apply a little bit higher working load, so it can provide an excessive settlement. So it cannot reach up to the failure state. Okay. So design requirement, one of the following design method must be used for shallow foundation. Okay. So we have here direct, indirect, prescriptive. Okay. So carry out separate analysis for each limit state, both ultimate and subfeasibility. Okay, so this is what we call as a common type of calculation, okay, to carry to determine the ULS and also the SLS. Okay, so then we have the indirect, use comparable experience with result of field, laboratory, and observations. Okay, choose SLS loads to satisfy requirement of all states. Okay, so this is after we do the design and then construct the building, and then sorry, during the we may do the observations. Okay. So prescriptive, use conventional and conservative design rule and specified control of construction. Okay, use presumed bearing resistant. Okay, so normally for this type of methods, okay, so we may apply for a certain factor safety, okay, in order to have a very suitable load to be applied on the soil. Okay. So ultimate limit state, okay, it implies the application of partial factor of safety. Okay, P is the partial factor of safety to action or effect of action to obtain the design action and to the geotechnical parameter M or resistant to obtain RD, okay, design resistant. Okay, so the ED is to obtain the design action, okay, and then we may include what we call as the geotechnical parameter and also the resistant, okay, to obtain the RD. And definitely the RD should be greater than the obtain action to obtain. Okay, so this is the way how the EC7 work. Okay, so then we have another approach. Okay, subversivity limit state. Okay, need to check for the CD is the limiting value of the effect of an actions. Okay, so then it should be compared with the EV. Okay. Okay. So this is the design action. Okay, can be represent. Okay. Um, by okay, here we have the parameter. Okay. Uh, this is permanent loads. Okay, and then we have the variable loads. Okay. So then we may multiply, okay, with a different characteristic of a permanent loads and also different characteristic of the variable loads. Okay. So I will show you, okay, in the example, okay, how we apply for this design action, okay, using the EC7. Okay. Okay, so this is the design action. Okay. So then for the design assistant, okay, so we may use this approach, okay, as we have discussed previously, okay, for Malaysian use, okay, we may use the design approach number 1. Okay, so under the design approach number 1, okay, there will be a combination of A1, M1, and R2 for combination number 1, and there will be another combinations, okay, which is A2, M2, and R1, okay, for design approach number 1. Okay, so two condition, either drain or undrained. Okay, so the difference between the EC7 and the British standard, okay, so it differentiate between the sand and soil, sand and clay, based on the behavior of the soil. Okay, for example, for drain, okay, so it represent sand, while for undrained, it represent for clay. Okay, because sand is capable to drain very fast. Okay, when we uh, pour a water, okay, inside on the sample on the sand material compared to the clay. Okay, so SLS check the performance of the foundations. Okay, so means ULS is to check the failure condition, and SLS to check the performance of the foundation. Okay. Okay, so this is the partial factor safety to be used, okay, for the shallow foundation. Okay. Uh, okay, for the action, okay. So for the action, design action, okay, we may refer to the permanent and variable. Okay, so under a British standard, okay, the permanent is referred to the dead load, variable is referred to the life load. Okay, so then we have unfavorable and favorable. Okay, so unfavorable means that the thing that we doesn't want to be included, or the conditions that we doesn't want, that we most hated. Okay, so for example, if the failure, okay, settlement, so we consider as a unfavorable. Okay, so normally in design, okay, we choose the unfavorable because we want to measure what will be the most critical action should be that could be sustained by the structure. Okay, so then for the design resistant, okay, we should include the soil properties. Okay, so in the soil properties, okay, So we may include all these parameter. So we have tangent, we have tangent phi. Okay. So they are a little bit different with a common uh, approach using the BS. Okay. So if BS, we are using only the tangent value. But in EC7, they use the tangent phi. Okay. So means that if we want to get what we call as the NC, NQ, or N gamma for the shallow foundation, okay, so we need to apply a tangent first, okay, in order to get the actual phi value, okay, uh, to get the NC, NQ, and N gamma, okay, because this tangent phi, okay, the phi is the actual value for the what we call for the soil, okay. Then we need to apply the tangent, okay, to get the value for the phi itself later. Okay, I will discuss later in the example. Okay, then we have effective cohesions, we have undrained strength and confined strength with density. Okay, so for a combination number one, there will be no problem for the tangent phi because it divide with one. Okay, the problem is when we use the combination number two, okay, so we need to uh, divide, for example, tangent phi over 1.25. Okay, that is the factor safety. Okay, then we need to apply the tangent to get the phi value later. Okay, so it will be a little bit different. Okay, for example, if 30 divide with 1.25, okay, and tangent 30 and a tangent 30 divide with 1.25. So slightly different, okay, between this value and this value. Okay, so there we have need to be careful that we are not using the phi but we're using the tangent phi. Okay, so then the other one is the what we call as the resistance. Okay, uh, for example, for bearing capacity, then we may apply the R1. Okay, for sliding, we also apply the R1, which is equal to 1. Okay, so the M2 have two condition there. Okay, for example, if the M2, if the shallow foundations is located not on the slope and embankment, so we are using the M2. Okay, so if the shallow foundation located at the slope and embankment, so we are using this M2 asterisk. Okay, so this is R4. R4 is used in the deep foundations. Okay, okay. So to have a better understanding, we may go for the example letter. Okay. Okay. So this is for the bearing resistance. Okay. So VD must include weight of foundation and any backfill above it. Okay. Design action VD variable vertical load, permanent vertical load, supported permanent load, weight of foundation, weight of backfill, load from water, pressure, and also uplift. Okay. So this is the input for the design loads. Okay. So some consideration for drain condition, water pressure must be included as action. Okay. How to apply to the partial factor safety to the width of the submerged structure. Okay, since the water pressure add to reduce VD, so it may be considered as favorable, while the total width is unfavorable. Okay, so physical, the soil has to sustain the submerged weight. Okay, for the design structure member, water pressure may be unfavorable. Okay, so this is for the water pressure. Okay. So for the sliding resistance, okay, so this is the consideration that we need to put. Okay, however, I didn't have the discussions on the sliding resistance in the example letter. Okay, so this is more related to the design of retaining structure. Okay. So this is for the drain condition. Okay, so RD should be calculated as the ground resistance as follow. Okay, for the what we call as for the drain condition for the sliding resistance. Okay, so this drains uh, condition where we use the same assumption of the friction between wall and soil, or the friction between material and soil. Okay, by using this column friction between wall and soil parameter or formula. Okay. So then for the undrained condition, okay, the shearing resistance RD, okay, should be calculated as AC DUD. Okay, so that is for additional information for the shearing. Okay, for the shearing resistance. Okay, so some consideration, maximum sliding will occur with little movement of RD and RPD, okay, which will cause difficulty in mobilizing both magnitudes. Okay. So remodeling effect of excavation, erosion and shrinkage passive resistance should be neglected. Okay. In some circumstances, the vertical load in undrained condition is insufficient to produce full contact between soil and foundation. Those the design resistance should be limited to 0.4 VD. Okay, so that is some explanations on the shear resistance. Okay. Okay, so now we look on the bearing problems. Okay, so this is the common bearing capacity factor. Okay, that been proposed by Meyerhoff. Okay, however, in EC7, okay, there is slightly difference between the Meyerhoff, what we call as Meyerhoff equation, with this EC7 approach. Okay, so we can find that there is no depth factor included in this formula. Okay, so we only have a shape factor and also inclination factor. Okay, so bearing capacity in drain material is generally expressed as, okay, as this equation. Okay, so this is based on the drain condition only. Okay, so if a drain fully drained or fully sand, so there will be no NC value later on. Okay, so bearing capacity factor related to self weight, bearing capacity factor related to cohesion, S gamma and SC shape factor, value of NQ is found by limit analysis and given by the closed form. Okay, so this is the formula for the NQ. Okay, so then for the NC, we can use this formula, and also for the N gamma. Okay, so there will be another approach. Okay, by using what we call as by using a chart. Okay, to determine the NC, NQ and N gamma. Okay, so the sample method given in MSEN 1987 omit depth. Okay, so they are not consider the depth, and ground inclination factor, okay, actually they consider, okay, the ground inclination factor, okay, but they include what we call as eccentricity as well in the in the in the inclination factor, okay, which are commonly found in bearing resistance formulation. Okay, the omission of the depth factor is on the side of safety, but the omission of the ground inclination factor does not. Okay, so to determine the ground inclination factor, one of the method which may be considered in described in foundation and earth structure design manual will be mentioned in the next topic. Okay, so actually they include the ground inclination factor in the what we call as in the equation, in the formula. Okay, so okay, so this is the shape factor. Okay, then either we use this calculation or we can determine from this what we call as this graph. Okay, so this is the inclination factor. Okay, they include the IC, IQ, okay, IQ, okay, and also they have the eccentricity as well. We call as M. Okay, so this is the how they define the M. Okay, based on the L and B. Okay, so before we can define the B, what we call the D prime and L prime, so we need to determine what is the E. Okay. So we need to determine the E. Okay. So the E is to get the E, so it is based on the moment. Okay, I will discuss later on. Okay. So it is stated that the vertical load action should include the weight of any backfeed acting on the top of the footing in addition to the weight of foundation itself plus the applied load carried. Okay, they will be explained further in the next sessions. Okay, especially in the what we call in the example later. Okay. Okay, so this is the chart, okay, to get the value for the NC and QNN gamma, okay. So then there we have a degree of the soil, okay. So this is the bearing capacity factor, okay. Okay. So, okay, for the water condition, okay, it is vital that appropriate value of unit weight are used in the bearing capacity equation. In an effective stress analysis, three different situations must be considered by assuming no inclination. Okay, so in the water, if the what we call the shallow foundation, okay, has a different height of water. Okay, so we need to consider these three different situations. Okay, so if the water table is below the foundation plane, okay, so let me draw first. Sorry, yeah. Okay. The bar unit weight to be used is the second and third terms of the equation. Okay, is below the foundation plane. Okay, for example here. Okay, so the bar unit weight, the okay, I guess this is if the water table is far below. Okay, is far below. Okay. How to determine how far is it? Okay, so normally, okay, if the water table is from the what we call from the foundation base, okay, is greater than the width of the foundation, okay, so we may not consider the effect of the groundwater level, okay. So means that we may use the same unit weight, okay, unit weight for unit weight of the soil, okay. For example, uh, this is contribute to the sub-equation number 2, okay. For the sub-equation number 2, so it is on the NQ, eh? So this is for the NQ, okay. While for the sub-equation number 3, okay, it is for the N gamma, okay. Okay, so that is condition number 1, okay. So if the water table is at the foundation plane, okay, so if at the foundation plane and to the width to the within the height of the width of the uh, uh, footing, okay. So the buoyant unit weight must be used in the third terms of the equation, okay. So the N gamma, okay, have some the gamma in the N gamma, the sub equation number 3 has some little bit modification by using the effective unit weight value, okay. So the bulk unit weight should be used in the second term of the equation. So no changes on the sub equation number 2, where we still use the what we call as the same unit weight, okay. So the last, if the water table is at the ground surface and above the foundation base, the effective unit weight must be used in the second and the third term of the equation, okay. So means that in the third situation, we should use the effective unit weight and also effective unit weight for the second and third, okay. Okay, calculation procedure for shallow foundation on undrained and drained material using limit state design, okay. Total stress or effective stress analysis, determine the shear strength parameter or effective stress parameter and unit weight of the underlying soil to determine the bearing capacity factor, okay. So then we have there a groundwater table. For an effective stress analysis, the groundwater table will be give an impact to bearing capacity, okay. So ultimate limit state evaluation depends on type of footing analysis using design approach 1 only. Determine the size of footing initially, okay. So this is the procedure. Check the combination between A1, M2 and R1 and combinations of A2, M2 and R1. Okay, the last is check on stability, serviceability limit state. The allowable bearing capacity may be have to be downgraded due to the local building code of practice or lower bearing pressure to avoid excessive settlement allowed. Okay. However, for this topic, I only discuss on the bearing capacity. Okay, not include the stability limit state. Okay. So that is by using the direct methods. Okay. I will discuss on the example. Okay, later on. Okay, how we calculate for the bearing capacity using this EC7. Okay. So another approach, okay, by using the bearing capacity from another approach to determine the bearing capacity by using the SPT value. Okay. So first, how to convert N value, okay, to N70. Okay, so this is the corrected N70 value, okay, that we may use in the design later on to get the bearing capacity for the shallow foundations. Okay, so the N70 is equal to Cn times nu1 times nu2 times nu3 and times nu4. Okay, so the nu1, nu2, nu3, nu4 can be is the equipment consistent, and we can use as 1. Okay, and the Cn is the equation with where 90.76 over effective vertical stress power by 1 over 2. Okay, or it is a square root. Okay, so so change from of N70 to the other. Okay, so this is how could we later on change to the other N corrected value. Okay, because some of the standard they use the N60. Okay, some of the standard use the N55. Okay, so and there are also some standard using the N45. Okay. So this is how we can change the what we call is the N70 to the other standard. Okay. Okay, then okay, this is how could we estimate the bearing capacity, okay, from the SPT value. Okay, so widely used to obtain the bearing capacity of the soil directly. So Meyerhoff used for computing the allowable bearing capacity factor for a 25 millimeter settlement. Okay, so there we have a QA equal to N over F1 times KD. Okay, so to use this equation, B should less or equal F4. Okay, so then we have there another one, QA is equal to N over F2. Okay, times B plus F3 over B power by 2 KD, okay, where the B should greater than F4. Okay, so QA is allowable bearing capacity for what we call as for the differential settlement 25 millimeter. Okay, so the KD is 1 plus 0.33 D over B and should less than 1.33. Okay, so the factor F convert Mayoff origin equation to allow a 50% increase in bearing capacity and to produce KPA. Okay. So that is how we estimate the bearing capacity from the SPT. Okay, so this is the value for the F1, F2, F3, and F4. Okay, so the F4 that we refer here is is the value of 1.2. Means that the B should less than or greater than 1.2 to differentiate between the first and second equations in this example. Okay, so need to check the comparison between B with the F4. Okay. Okay, so for this case, this is based on the N55, okay, the corrected N55. So then we may determine the what we call as the value for the QA, okay, okay, allowable bearing for surface load footing with settlement limited to approximately 25 millimeter. Okay, so this is the B value. Okay, the B is hidden here. Okay. Okay. So if the B is greater than 1.2, so the curve, this is B is less than, this is B. Okay. So if the B is less than 1.2, it provide the same, what we call as the same value of the bearing capacity. Okay. So if the B is greater than 1.2, so it show a difference of uh, reduction of QA. Okay. So either we can use this formula, okay, or we can use this formula to get the QA without referring to the graph. Okay. Okay. So from equation N55 or N70, okay, is the statistical average value for the footing influence zone about 0.5 B above footing base to at least 2 B below. Okay, this is taken into account somewhat formats where Meyerhoff obtained QA equal to N55 over N70 over F2 times KD. Okay, so this is the where the B plus F3 over B power by 2 approximately equal to 1 format and is neglected. Okay, in this equation, the allowable soft pressure is for the assume of 25 millimeter settlement. Okay, in general, the allowable pressure for any settlement is delta Hj over delta H naught times QA. Okay, where the delta H is equal to 25 and delta Hj is the actual settlement that can be tolerated in mm, such as 50 millimeter normally for mat foundation. Okay, so this is the approach to get the value for the QA for the mat foundations. Okay, so then for the sand, okay, by using the SPT, okay, so this is the value for the QA, equal to 30 times N55. Okay, where N55 is the average SPT value of about 0.75 B below the proposed base of footing. Allowable bearing capacity, bearing pressure QA is complete for settlement checking as well. Okay, so this is for the QA equal to N55 over 15B. Okay, for delta H naught equal to 20. Okay, use a linear ratio to obtain QA for settlement, which is now equal to 20. Use smaller of the computed value from the above equation for the design. Okay, so that is how we determine the QA or the allowable bearing capacity by using the SPT. Okay. So there will be another approach by using the CPT, okay, bearing capacity from CPT. Okay, so the bearing capacity used from Terzaghi equation can be estimated using the 0.8 and Q or 0.8 and gamma or equal QC, where QC is the average depth interval from B half to 1 B below the footing. The application should be used for DB less than 1.5. Okay, so for cohesionless soil, okay, the value for the slip ultimate bearing capacity, okay, by using the approximate QU, okay, from here, okay. So then 28 minus 0.0052 times 300 minus QC, okay, power by 1 over 5. That is for the strip. And for the square, that is the value, okay, that should be used to get the QU ultimate. Okay. So for the clay, okay, this is the formula for the clay, okay, 2 plus 0.28 QC for strip, and for the square Q equal to 5 plus 0.34 QC. Okay, so that is for the CPT. Okay, so we have learned on the direct approach. Okay, so and then we have learned on the indirect approach by using the SPT or by using the CPT value. Okay, so we will move to the example part. Okay, to discuss on the use of the direct approach. Okay, using the EC7 to determine the ultimate bearing capacity value. Okay. Okay. So I will share this example in your what we call in your e-learning. Okay. So you can go through this book. Okay, it's very good to understand on the bearing capacity. Sorry, on the bearing capacity using the Eurocode. Okay, so I only focus on the shallow and deep foundation for this part. Okay, so it only focus on the chapter number chapter number 8. Okay, so you can have a read. Okay, to understand on the bearing capacity of soil. Okay, so they discuss on the ultimate bearing capacity, safe bearing capacity, allowable bearing capacity. Okay, type of foundation we have there: strip, pad, rough. Okay, and pile foundation. Okay, pile foundation when we discuss next week. Shallow, deep. Okay, so this is how the evolution of the ultimate bearing capacity for the shallow foundation based on the theory. Okay, first they discuss on the earth pressure concept. Okay, so then slip circle methods also has been discussed. Okay, combine of and sector, this is another type. And then the one that we use now is under the plastic failure theory. Okay, so under the plastic failure theory, we have the general shear failure, local shear failure. Okay, so this is the general shear failure that we assume that uh, the soil is fully mobilized. Okay. Then we have punching shear failure. Okay, so Prandtl analysis. Then we have the Terzaghi equation. Okay, so the one that we discussed is using the Meyerhof. Okay, so this is the example based on the conventional equation. Okay, so you may look later on. Okay, this is the use of the factor safety. Okay, which is the conventional approach. Okay, F. Okay, then the discussion on the effect of groundwater on bearing capacity. Okay, so you can do some reading here. Okay, development in bearing capacity. Then from there, they propose for the Meyerhof propose the equations. Okay, so in this example, they have a depth factor. Okay, the D. But in the EC7, okay, the D is not been covered, the depth factor. Okay. So this is the NC, NQ, and gamma, the shape factor, depth factor. Okay, so this is example based on the Meyerhof. We can go through later. Okay, then the effect of eccentric and incline loading on foundation also has been discussed here. Okay, so this is the how we determine the L and B prime. Okay, so the B prime is equal to B minus 2E. So we need to identify what is the value of the E. Okay, so the value of the E could be calculated based on this formula. Okay, magnitude of the eccentric load. Okay, weight, self weight of the foundation. So there will be an example. I will discuss how to determine the E later on. So then incline loads, okay, also been included in the Meyerhof. Okay. So for example, if we have a vertical and horizontal load, so we need to determine what will be the P value due to the PV and pH. Okay. Okay, now we look on the Eurocode 7. Okay, so the design of spread foundation is covered in shallow in section 6 or Eurocode 7. So they call as a spread footing, not as a shallow foundation. So the limit state to be checked and partial factor safety to be partial factor to be used in the design are the same as we saw when we look at the design of retaining wall. So this is in section 7. So in the example, no section 7 or no chapter 7 has been included. Okay, in terms of establishing the bearing resistance, the code state that a commonly recognized method should be used. Okay, and Annex D of the standard give a sample of calculation. Okay, interestingly, the depth factor are excluded in Eurocode 7. Okay. So the author also mentioned here without explanation. So I could not explain why the depth factor is not being included in Eurocode 7. And for this reason, they are excluded too. Okay, okay, from the solution 8.5 and 0.6 in this chapter later on. Okay. However, offer the choice whether to include the depth factor or not. Okay. So while the design procedure required to satisfy the condition of Eurocode 7 involve essentially the same method as we have seen so far in this chapter, there are few different listed in Annex D which can be considered for drain condition. For this concern the shape inclination factor as well as the bearing resistance factor and are listed below. Okay, so this, the difference there is no depth factor. Okay. However, they do some improvement on the I, where we can include the what we call it, we can include the eccentric issue, okay, for the I. So this is the eccentric, okay, to determine the eccentricity effect. Okay. So the E7 also stated the vertical load should include the weight of any backfill acting on the top of the foundation, in addition to the weight of the foundation itself plus the applied load it is carrying. Okay. So this is example 8.5. Okay. So we look on this example. Okay. Continuous footing. So means that it is strict footing. So means that the length is very huge compared to the width. So we can consider L is equal to infinity. Okay. So the B is 1.8 meter. Okay. And the thickness is 0.5. Okay. It is founded at the depth of 0.75 in clay of unit weight 20 with phi 0 Cu 30. The foundation is to carry a vertical line load of magnitude 50 kilonewton per meter run, which will act as a distance of 0.4 meter from the center line. Take the unit weight of the concrete as 24. Okay. So, so there are eccentric problems here, okay, where the distance is 0.4 from the center. Okay, so determine the safe bearing capacity for the footing, taking F is equal to 3.0, and then we also need to check by using the Eurocode 7. Okay, limit state by establishing the magnitude of the over design factor. Okay, so the first one is by using the factor safety 3.0. Okay, so what should we do? We need to determine the E. Okay, so this is how we determine the E. Okay, safe weight of the foundations. Okay, 0.5 is the thickness of the foundation times 24 is the unit weight of the concrete times 1.8 is the width of the footing. So then 25.6. Okay, weight of the soil on the top of the foundation. Okay, so because the soil has been, the foundation has been installed or built, has been installed at the depth of 0.75. Okay, so after we minus the thickness of the foundation 0.5, so the thickness of the soil layer is 0.25. Okay, so time with the unit weight 20 times with the width 1.8, so we obtain 9. So the total weight of the foundation and soil, then we obtain 30.6. Okay, so eccentricity of bearing pressure E is equal to P times EP over P plus W. So 50 times 0.4. EP is 0. EP is the distance from the center. See, 0.4 over 50 plus 30.6. So the E is equal to 0.25. Okay. So in order to use the L prime value, so we need to check with the B over 6. Okay. So when we check, 1.8 over 6 is less than 0.25. So the total force acts within the middle third of the foundation. Okay. So then the effective width of the footing is equal to 1.3. Okay. So from the table 8.1, okay, for the phi is equal to 0. So then NC, NQ, and N gamma we can get from the table 8.1. Where is table 8.1? So we need to move to the previous page. Okay, so this is the table 8.1. So 1.141 and 0. Okay, so this is for the drain problem, sandy soil. Sorry, this is for clay soil. Sorry, this is for undrained because the phi is equal to 0. Okay, clear. Okay, so then footing is continuous. So L is equal to what we call as infinity. Okay, so then we calculate for the DC. So we need to look on the formula for formula. I guess we can use the Zagi. Oh, this is your Meyerhoff. So you need to look on the formula. Okay, get the value for the SC and DC. Okay, so because the value of the N gamma is 0, so there will be no sub-equation number 3. Okay, only sub-equation number 1 and sub-equation number 2. Okay, so then safe bearing capacity, so they divide with 3 later on. Okay, so once we divide with 3, so they can get the safe bearing capacity is equal to 75 kPa. So this 75 kPa should be timed with the B prime, okay, to get the actual bearing capacity due to the eccentric problems. So the value is 97.5. So means 75 times 1.3. Okay, so that is for the first example. Okay. Okay, wait. Okay. So then we look on the Eurocode 7 geo limit state combination number 1. Okay. So from table 1.7 okay, because we are designed for the failure condition, so we may use for the unfavorable. Okay, and we only been provided with the dead load. Okay, no live load. Okay, so when we look on the table, we are not given with the table. 7.1 not been given here. So we may look on the previous table. Okay, so previous table in the slide. So we look on the table. Okay, here. Okay. So when we look on this table, okay, so they only provide for the permanent. Okay, and then we consider on the failure condition. So we look on the unfavorable. Okay, so the value that we should use for the permanent is 1.35. Okay, so there are no variable or live load, so no need to use 1.5. Okay, so then we are given with the cohesive value, so we use for the M1 for the combination number 1. So later on we may look on the combination number 2. Okay, so then we only refer to the bearing problems for the split footing, for the shallow split footing. So we use the R1 is equal to 1. Okay, so we come back to the example. Okay, so 1.35, 1.511. Okay, so then for the design material, okay, 30/1 is equal to 30. Okay, so that is for the CU. Okay, so then for the design action, okay, the width of the foundation, W times 1.35, we obtain 41.3. Apply line load. Okay, the load that the load that apply on this on the foundation is 50. So 50 times 1.35, so we obtain 67.5. Okay, so this is the partial factor that we have applied. Okay, so for the action we multiply, for the material we divide. Okay. And also for the resistance, we may multiply, we may divide as well. Okay, so then for the effect of the design action, okay, so this is the design action FD. Okay, so the value is equal to 108.8. So later on we may compare with the RD. Okay, so then eccentricity, okay, the same procedure, but for this case we use the PD. Okay, times EP times of over PD plus WD. Okay, so then we obtain 0.248. Okay, so since the E less than B6, so then the B prime is equal to 1.3. Okay, so for the design resistance, NC is equal to 5.14. There will be no difference. Okay, 1.0 and gamma 0. So SC is equal to 1. So the ultimate bearing capacity for this case, okay, is equal to 30 times 5.14 times 1 plus 20 times 0.75 times 1. So we obtain 169.2. Okay. So that is for the ultimate bearing capacity. Okay. Ultimate bearing capacity or load in terms of load value per meter run. So 169.2 should be multiplied with 1.3. Okay, so we obtain 220. Okay, so the bearing resistance is equal to 220/1, which is the gamma RV. So we obtain 220. Okay, so the difference between the RD and FD, so means that the RD is greater than FD, so it is already satisfied with the Eurocode 7. In terms of ratio, so the RD ratio over FD is 2.03, which is greater than 1. Okay, so that is for the combination number 1. Okay, so then we have here combination number 2. Okay, so for the combination number 2, okay, we may look on the table. Okay, so for the combination number 2, in here we have permanent unfavorable 1.0. Okay, okay. For combination number 2, okay, we use the unfavorable equal to 1. Okay, and then because these problems, okay, is okay. So okay, based on Smith, okay, this is a little bit different. Okay, so this is based on Malaysian standard MSE EN7. Okay, so when we look on the combination number 2, M2, which is other than slope and embankment. Okay, so we may refer to the uh, okay, 1.2. Okay, actually same, sorry. Uh, Means that the MS standard for the Malaysian and also for the Eurocode, okay, so it gives the same partial factor value because the Smith uh, is using the EC7, okay, and for this example, okay, when we look on the MSEN7, okay, there will be no difference between the partial factor safety. However, in a pi design, okay, there will be a little bit different, okay, between the EN7 with the Malaysian standard EN7. Okay, so for example, for this case, the M2, okay, for the CU, okay, effective cohesion. Sorry, for the undrained strength, okay, we are using the undrained strength because the water is far. Okay, so the undrained strength is 1.4. Okay, and the same with the Smith 1.4. Okay, and gamma RV is 1.0 because it is stated in the R1. Okay, so we are using 1.4, and 1. Okay, so 1.3 is not being used, okay, because we doesn't have any live load. Okay, and then gamma CU is 1.4, gamma RV is 1. Okay, so the same procedure, just repeat the same procedure, get the E. Okay, E is 0.248, B prime is 1.3. Okay, so then later on the value is 1.3.1. Okay, the RD is the ratio between the RD and the FD is 2.02. Okay, little bit similar with the combination number 1, which is 2.03. Okay, so means that both of combination number 1 and combination number 2 greater than 1, so the geo limit state requirement is satisfied. Okay, so that is for the first example. Okay, so we have another example here. Okay, so a concrete foundation 3 meter wide, 9 meter long, and 0.75 meter deep is to be founded at a depth of 1.5 in a deep deposit of dense sand. So this is under a drain situation. The angle of shearing resistance of the sand is 35 and its unit weight is 19. Okay, the unit weight of the concrete is 24. Okay, using a lump factor of safety, okay, 3.0, determine the bearing capacity of the foundation. Okay, determine the safety factor the safety bearing capacity of the footing if subjected to vertical. Okay, so it has an inclination here. Vertical of 220 and eccentricity of 0.3 together with horizontal line load 50 acting at the base of the foundation. So it is illustrated here. Okay, 20, 22, 0 and 50. Okay, so then they are a distance of 0.3. Okay. So for situation in number 2 above, establish the magnitude of the over design factor for Eurocode limit state using design approach 1. Okay, so so this is the procedure for the lump factor safety. Okay, so you can go through later on. Okay, where the C value is not provided because the C is equal to 0 because it's sand, so it doesn't have any NC. Okay, in our example. Okay, so then we have phi 35 and Q and gamma. Okay, 33.3, 48.03. So this is the SQ, S gamma, DQ. Okay, so from there we need to get the safe bearing capacity 855.7. That is without eccentric problems. Okay, then we move to the eccentric problem. Okay, the same procedure, get the E from E, compare with the B over 6. Okay, so B prime, so we obtain 2.52. So then to get the alpha towards the vertical, okay, so we need to get first the force. Okay, so use the square root B square plus C square. Okay, and then to get the alpha is the ratio, is the tangent of 450 over 2466. Okay, so you need to draw uh, yeah, you need to get the alpha value. Okay, let me show. Okay, to get the alpha value here, what should you do? Okay, this is the vertical. Well, this is the horizontal. Okay, so then you get the inclination value. Okay, so this inclination value, for example, hypotenuse line. So you need to get this alpha. Okay, so this we call as inclination I. Okay, so tangent H over I. Okay, so then you can get the alpha value. Okay, okay, so then that is the alpha. So just calculate all the factor I, Q, I gamma, SQ, S gamma, DQ, D gamma. Okay, from there we calculate later on the safe bearing capacity. Okay, by divide with 3. Okay, so we get 530. Okay, so that is for the conventional approach. Okay, for the Eurocode 7, okay, the same procedure. Okay, for the first one, okay, we get the WS because we want to get what we want to multiply with the partial factor value. Okay, so in here we have 1.35, the partial value for the permanent. This is for the variable, and this is for the material. For the fee, so this is for resistance. Okay, so as I discussed previously, okay, so we cannot divide 35 with 1. Okay, so we need to use the tangent 35 over 1. So to get the phi value, so we need to tangent the formula. So 35, so because it divide with 1, so it doesn't change. However, it will change little bit different, okay, when we divide with 1.25. Okay, so we cannot get a straightforward tangent pi over 125, then a tangent similar with 35 over 1.25. So you can use your calculator, so there will be a slightly difference. So although it's slightly different, your NC, NQ, and N gamma will have a different value later on. So it can make an error when we want to calculate for the last value for the resistant design. Okay. So then this is for the width of foundation apply. We just multiply 1.35. Okay. So then that is for the FD. Okay. So for this case, they only calculate for the sample number B, for the second question for the eccentricity, not for the first. Okay. So then we'll get the E. Okay. From the E 0.208. Okay. From there we get the B prime and also for the A prime, the area. Okay. So from table 8.1, okay, the NCU and NC and NQ, okay. So then we may obtain N gamma, okay, in the based on the formula, okay. Okay, from table, okay, 0.1, okay, or from Eurocode, so there will be a slightly different between the sorry. So NC we are not used because sorry, NC here. NC we have NC there, but there will be no C value, so no need to bother on the NC. So NQ and N gamma. Okay, so that is for SQ, SC, and S gamma. Then this is how we get the M. Okay, so B prime over L plus 2, okay, and then B prime over L plus 1, so we get 1.78 to be included in the inclination factor. Okay, so then we put the IQ, IC, and also the I gamma. Okay, so that is for the inclination factor value. Okay, later on we just include all the information in the formula. Okay, so divide with the RB, so we obtain 38,853. Okay, we divide with the FD, so this is the ratio between the resistance with the action load, so we obtain 10.1. Okay, so the value is very huge. Okay, however, it already satisfied with the geo limit state requirement. Okay, so then we move to combination number 2. Okay, I guess the same procedure. Okay, this is what is the difference. So if you use your calculator, 35 over 1.25, so you will get, let me calculate, 35 over 1.25. So we get 28. Okay. So but by using this approach, we get 29.3. So it's very huge different, 1.3 different. So what happen if we use to determine the NQ, NC, and N gamma? So we will have a different value of NC and NQ and gamma later on. Okay. So we repeat the same procedure. Okay. And from there we can get the value between the over design factor, which is 6.19. So since the over design factor is greater than 1, the Joule limit state requirement is satisfied. Okay, so that is all for the bearing capacity of a split foundation or shallow foundation. Okay, so this is example or discussion on a layer of soil. Okay, non-homogeneous soil condition. Okay. Okay. So we not discuss it in our discussion. Okay. So in situ testing for ultimate bearing capacity. Okay, this is the sum of methods, okay, to determine the bearing capacity by conducting at the site. Okay, this is SPT correction that we have discussed previously. Okay, estimation. Okay, the same what we call the same graph from the slide. Okay, so this is example for the SPT correction. Okay, take a look. Okay, CPT. Okay, then the last topic is on the pile foundation. Okay, so that is all for today. Okay, I will share this note and also upload the video in the e-learning. Okay. Okay. So we meet next week. Okay. So Assalamualaikum and good afternoon.
Alaikum salam. Thank you so much. Goodbye.
Goodbye.